In the previous lecture, we discussed about the binary detection process with unipolar signaling. In unipolar signaling, we have a binary 0 represented as 0 volt and a binary 1, a bit 1, represented as some positive voltage, which we denote as A volt. So the bit sequence here is 1 0 1 0 1 0, right? So we are representing a 1 as a positive voltage and a 0 as 0 volt, and to this, when noise gets added, the received signal looks like this blue waveform, which is the transmitted signal, the red pulse waveform, plus the noise waveform, which is Gaussian noise. Okay, so when Gaussian noise gets added to the transmitted waveform, we see random variations about the transmitted voltage level. Now the PDF of the received signal is shown on the right hand side here, where the one in the blue is the PDF of the received signal when a 0 is transmitted, and the red PDF corresponds to the PDF of the received signal Y when a 1 is transmitted. So let me write that down. So that's the probability of the received signal Y on the condition that 0 is transmitted. So it's a conditional probability. And the red one is the PDF of the received signal Y when a 1 is transmitted. So we have seen this in the last lecture, and from the PDFs we notice that because when a 0 is transmitted, we are transmitting 0 volt. To 0 volt the noise gets added, so the received signal PDF is the same as the noise PDF, centered on 0 with a mean value of 0. But when we transmit a 1 to the 0 mean Gaussian noise, a constant value of A is getting added. So the PDF of the received signal is the noise signal shifted to the right by A, so it is now centered on A. And then we determine the threshold as the intersection of these two PDFs, which is exactly halfway between 0 and A, so at A by 2, because of the symmetric nature of the Gaussian PDFs. Now, the error probabilities corresponding to a 1 and 0 are these areas. So that's the error probability corresponding to 0. So when you transmit a 0 and the 0 becoming a 1 is this shaded region, which we call as PE0, and then to the left of the threshold, under the PDF for the received signal when a 1 is transmitted, the area under that to the left of the threshold represents the error probability when a 1 is transmitted. And we did the computation for all of this, and we finally got the average error probability for unipolar signaling as by the way, let me write this is unipolar. Okay, and for unipolar we got the average error probability as PE is equal to the Q function of A by 2 sigma. So that's the expression we had in the previous lecture. In today's lecture, we are going to do a similar analysis for polar signaling. So polar signaling. In polar signaling, we represent a bit 1, so that's a 1 here, a 0, a 1, 0, 1, 0. We represent a bit 1 as some positive voltage and a bit 0 as some negative voltage. So we are going to represent a 1 as a positive voltage, which we will call as A by 2, and a 0 as a negative voltage, which we'll call as minus A by 2. Now the choice of this A by 2 is just to make a reasonable comparison with our unipolar case. In the unipolar case, we chose the voltage separation or the level separation between 0 and 1 as A volt. The distance between them is A volt. So because we want to compare the unipolar and polar, in polar we are going to choose the voltage levels such that the separation between them is also A. So we have polar now, that means we have a negative voltage and a positive voltage, but the distance between them is still a. From minus a by 2 to plus a by 2, the distance or the level separation is still a, right? So that's why we are choosing representing this as minus a by 2 and plus a by 2. Okay, so correspondingly the received PDFs are going to be, so let's write it down. So for polar signaling, we are going to represent the transmitted signal x, the transmitted signal, which we denote as x is equal to minus a by 2 for 0 and plus a by 2 for bit 1. So these are the two possible voltage levels that we are going to have for the transmitted signal. The received signal y is equal to the transmitted signal plus noise, which can be one of the two, which is minus, let me write it, plus noise, which is equal to, x can take on two different values. It is minus a by 2 plus noise when 0 is transmitted, or plus a by 2 plus noise when 1 is transmitted. So for the received signal we have two possibilities. It's either minus a by 2 plus noise or plus a by 2 plus noise, depending on whether 0 is transmitted or whether 1 has been transmitted. Now, as we know, the noise is the noise that we are dealing with is zero mean Gaussian noise. That means the PDF of the noise signal is a PDF which is looking like this bell curve, but centered on 0. The central value of the noise is 0. But to the zero mean Gaussian noise, we are adding minus a by 2. So whenever we transmit a 0, the conditional PDF of the received signal is going to be the noise PDF shifted and centered on minus a by 2. So the blue curve here, the blue PDF will be the noise, will be the conditional PDF of the received signal y when 0 is transmitted. So it has to be centered on minus a by 2. So that should be minus a by 2. That's where it is centered. And similarly, when bit 1 is transmitted, the received signal is going to be the noise signal shifted to the right by plus a by 2. So the conditional PDF of the received signal y when 1 is transmitted is the noise PDF shifted to the right by a by 2. So it will be centered here on plus a by 2. So as this label shows here, the blue one is for the conditional PDF of the received signal y when 0 is transmitted, and the red PDF corresponds to the received signal y when a bit 1 is transmitted. So we have this as P of y given 0, and this is P of y given 1. So now if you notice, the difference between the unipolar case and the polar or bipolar case is that in the unipolar we are representing the voltage levels as 0 and a for bit 0 and bit 1 respectively, and for polar signaling we have negative voltage minus a by 2 and plus a by 2 for representing a bit 0 and 1 respectively. In terms of the PDFs, what we notice is for bit 0 the conditional PDF is centered on 0, and when 1 is transmitted the conditional PDF is centered on a. But in the case of polar signaling, we see that these PDFs are centered on minus a by 2 and plus a by 2 respectively. Okay, and now we will proceed with the analysis in the same way as we did in the unipolar case. So we first have to make a decision threshold. So the decision threshold again is going to be the midpoint between minus a by 2 and plus a by 2. So the midpoint here is going to be, so that's the central value, the midpoint, that is 0. So that is going to be our threshold, so which will mark the threshold as this. So that will be the threshold which we will use for making our decision. If the received signal y is above the threshold, we will decide in favor of a 1. If it is below this threshold, we will decide in favor of a 0. So from the conditional PDFs plot, the threshold of 0 will be exactly at the intersection point of the two PDFs, which is halfway between minus a by 2 and plus a by 2, and they intersect exactly halfway between the voltage levels because of the symmetric nature of the Gaussian PDFs. So we will first define a decision threshold, then we will make a decision rule, and then we will compute the error probabilities for 0 and 1, and finally we will compute the average error probability for the entire data. So the intersection point here is going to be exactly at 0. So let's do the analysis by looking deeper into these PDFs and deriving the expression for the average error probability. So we have here our PDFs enlarged so that we can clearly mark out the different things. So the first thing is we define a decision threshold for our analysis. Decision threshold. So the decision threshold is the intersection of the two PDFs. Which is midway between minus a by 2 and plus a by 2, i.e. that is at 0. So the intersection point here is going to be exactly at 0. So that's our decision threshold. Then we have to make a decision rule. So the decision rule next is going to be, so using this decision threshold now, we will make a decision rule, which is something like this. If the received signal y is greater than the threshold, which is 0, the threshold is 0 here. If the received signal y is greater than the threshold, decide 1. If the received signal y is less than the threshold, decide 0. And that makes sense. So if you look at this threshold here, to the right of the threshold, the probability for 1 is having a big area. So there's a big area here which says the probability of the received signal being 1 is high on the right hand side of the threshold. Similarly, on the left hand side of the threshold, that is when y is less than 0, the probability of it being 0 is large, right? So that's the decision rule. And again, we are choosing this midpoint between minus a by 2 and plus a by 2 as our decision threshold because we consider the zeros and ones to be transmitted with equal probability. So if the received signal y is greater than this threshold of 0, we decide, the receiver will decide it's a bit 1, and if the received signal y is less than the threshold, then the receiver will decide it as a bit 0. And in the rare case where the received signal y is exactly equal to the threshold, then we have to randomly choose either as 1 or 0, and I'm going to put that equality for the 1. So that's our decision rule. Again, as a comparison with the unipolar case, in the unipolar case we had this as a 0 and this as a, and the threshold as a by 2. So everything has just got shifted in the in polarity now, because we now have it at minus a by 2 and plus a by 2, and the midpoint is now 0. So now we have our decision rule. Now once we have a decision rule, occasionally the transmitted bit could be 0, but the received signal ends up being above the threshold and the receiver decides it as a 1, so in which case there will be an error. So a 0 is transmitted and the receiver thinks it's a 1. So this area under this PDF to the right of the threshold, the area under the blue PDF to the right of 0 gives us the error probability when a 0 is transmitted. So that area here, that is the error probability PE. Let me write it outside. So that area here is the error probability when a 0 is transmitted, and similarly the area to the left of the threshold under the red PDF, that gives us the error probability when a 1 is transmitted. So we can now write down these expressions as PE0 is the area under P of y given 0. It's the conditional PD of y when 0 is transmitted to the right of the threshold, that is from 0 to infinity. So the area under a curve is integration, so it's integral 0 to infinity under the PDF when a 0 is transmitted under P of y given 0 dy. So that's the error probability for 0. Again, what we are going to do is we are going to represent that in terms of the Q function, and if you recall, the Q function is the area under the Gaussian tail when the Gaussian PDF is centered on 0. So now we see that this PDF is not centered on 0, it is centered on minus a by 2. So we'll have to shift this PDF to the right by a by 2 because it is centered on minus a by 2. So we have to shift it to the right by a by 2, so it comes and it becomes centered on 0. So we can rewrite this area as integral P of y given 0, and we want to shift it to the right, so it is shifted to the right by how much? By a by 2 dy. And when we shift it to the right, the limits of integration will also get shifted. So the 0 here will get shifted to the right by the same amount, which is a by 2. So when 0 gets shifted to the right by a by 2, it will become a by 2. A by 2. And infinity shifted further to the right is infinity. So we'll have it as the PDF shifted to the right by a by 2 so that it becomes centered on 0. So we are shifting this blue PDF, which is P of y given 0, to the right by a by 2 to make it centered on 0. So it's basically shifting this PDF to be made centered on 0. So the lower limit of integration, instead of 0, it will get shifted to the right and it will become a by 2. So we'll have it something like this. So let's say that's a by 2. So that area there will give us the error probability, and by definition the area under the Gaussian tail when it is centered on 0 is represented as the Q function. So that becomes equal to Q of a by 2 sigma. So it is Q of V by sigma. The V here is a by 2, so we get Q of a by 2 sigma because that's the area under the Gaussian tail, right? Q of a by 2 sigma. So it's this area that is being computed by this expression here. But this integral is basically representing this area, which is nothing but the Q function. So PE0, the error probability when a 0 is transmitted, PE0 is equal to Q function of a by 2 sigma. Similarly, we will compute the error probability when 1 is transmitted. So the error probability when bit 1 is transmitted is PE1, that is the area under the conditional PDF when a 1 is transmitted to the left of the threshold, which is this red area here. Again, we notice that it is not centered on 0. The red PDF is centered on plus a by 2, and to be able to write this as the Q function, we need to shift it to the left by a by 2 so that this red PDF becomes centered on 0. So PE1, let's write it initially as it is the area under this red PDF, which is P of y given 1, to the left of the threshold, that is from minus infinity to 0 dy. Now we want to shift it to the left and bring it or make it centered on 0. So shifting to the left is P of y given 1. Shift to the left means plus, and we want to shift it by a by 2 dy. And when we shift the PDF to the left, the limits of integration will also get shifted. We want to integrate from minus infinity to 0. So the limits will also get shifted to the left by a by 2. So minus infinity shifted further to the left becomes remains minus infinity, and 0 shifted to the left by a by 2 brings it comes to minus a by 2. So it will become minus infinity to minus a by 2. So the limits of integration are now minus infinity to minus a by 2, and that will be exactly equal to, and that is equal to integral P of y given 1 plus a by 2 dy. Minus infinity to minus a by 2 is the same as plus a by 2 to plus infinity by the symmetric nature of the Gaussian PDF. So now we have brought this PDF to the left and made it centered on 0, and we are computing this area from minus infinity to minus a by 2. So it's the area under the tail on the left hand side of the Gaussian PDF. Now, because of the symmetric nature of the Gaussian PDF, this area here is the same as the area on the right side. So these two are both equal. So minus infinity to minus a by 2, which is this area, is the same as this area, which is a by 2 to infinity. So hence we have written this minus infinity to minus a by 2 as a by 2 to infinity, because this area is equal to this area. So whether we calculate this or this, we are going to get the same answer. So you can now represent this as the Q function, right? So which is simply equal to the Q function of V by sigma. The V here is a by 2, so it's Q of a by 2 sigma. So we see that the error probability for the bit 1, or when a bit 1 is transmitted, is also equal to the Q function of a by 2 sigma. And what is a here? The a is the level separation between the bit 0 and bit 1. So this area and this area, they are both equal, right? So we can compute either of them and we can get the same answer. So to conclude, we get the error probability when a 1 is transmitted is PE1 is equal to Q of a by 2 sigma, which is exactly the same answer we got for PE0 as well. Now let's find the average error probability for the combined bits, because a sequence of bits, it will have both ones and zeros. So we know what is the error probability when we transmit a 0, and we also know what is the error probability when we transmit a 1. Next, we will compute what is the average error probability for a given sequence of bits which will have a mixture of ones and zeros. So we compute the average error probability which we call as simply PE, and that is equal to the probability that we transmit a 0 and there is an error in that 0, so it's P0 into PE0, or the probability that we transmit a 1 and there is an error in that 1. So we have already chosen our threshold by assuming that the probability of transmitting 0, that is P0, and P1 is same. That is, the bits 0 and 1 are equally likely to be transmitted. So for equally likely transmission of zeros and ones, that is P0 equals P1 equals half, then we can simply substitute this in our expression. P0 is half, and the error probability PE0 when a 0 is transmitted is Q of A by 2 sigma, plus P1 is also half, and the error probability when a 1 is transmitted is also Q of A by 2 sigma. So you can take this half as a common factor, so it's half into Q of A by 2 sigma plus Q of A by 2 sigma, which is half into, let me write it separately, so that's equal to half into Q plus Q is 2 times Q, so 2Q of A by 2 sigma, which is equal to Q of A by 2 sigma. Okay, a common mistake which I've seen students in the past make is that trying to cancel this 2 and this 2, right? This 2 is inside the function. Okay, you can't cancel this. Okay, so this 2 you can't cancel off this 2 with this 2 because this is the Q function of A by 2 sigma. It is an argument of the function, so you cannot cancel out what's inside the bracket here for the Q function. Okay, so that would be a big error. Please do not make that mistake. So we have the average probability of error PE is equal to the Q function of A by 2 sigma, right? This is the expression for the error probability for polar signaling that we are discussing now. And if you recall, we got exactly the same answer for unipolar signaling as well. So by looking at the error probability for unipolar and polar signaling, they look exactly the same, so it's difficult to make out which is better and which is more appropriate type of signaling to use for the communication purposes. But as it turns out, polar signaling is actually better than unipolar signaling. It has an advantage as compared to unipolar signaling. So when we analyze further and we do further techniques for Emery transmission as well, we will stick to polar signaling, and I will be illustrating how polar signaling is better than unipolar signaling in terms of the signal to noise ratio. So let us now do a comparison of unipolar and polar signaling and then try to understand which is better in terms of assisting the receiver's detection process and improving the error probability or minimizing the error probability. So in terms of the error probability expressions, they both look the same, but we need to dig a bit deeper to get a clear picture of which is better. So let's first write down the error probabilities. The error probability for both polar and unipolar is Q of A by 2 sigma. Okay, this is what we see for both of them, for both unipolar and bipolar. which we simply call as polar. Okay, now to understand what's the difference between them, we need to understand what this a by 2 sigma represents, because the error probability is a function or the q function of a by 2 sigma, and so the q function now depends on this a by 2 sigma. So we need to understand what does this a by 2 sigma represent in unipolar, and what does this a by 2 sigma represent in polar. So to understand that, let us first look at the unipolar case. In unipolar, we represent a 1 as a positive voltage, which is some A volt, and a 0 as 0 volt, right? A volt and 0 as 0 volt. So this is our voltage levels that we are using for the unipolar case. Now, if this is the voltage level that we are transmitting representing the bits for the transmitted signal, then we can compute the average signal power for the unipolar case. Average signal power, which we will define as SR. For the unipolar case, it's going to be the power when we transmit a 1 is the square of the amplitude, right? So it's A square. So whenever we transmit a 1, we are transmitting A volt. So the power corresponding to a bit 1 is A square by R. We'll choose the resistance value R as 1 ohm. So that's normalized to A square. And whenever we are transmitting a 0, it is going to be 0 square. So that's 0 square. And we want to take the average of these two. So it's A square plus 0 square by 2. So the average signal power when we are transmitting using unipolar signaling is SR is equal to A square by 2. Or in other words, we can write this as A square is equal to 2 times SR, or equivalently we can write that as A is equal to square root of 2 times the signal power. So this is for the unipolar case. Okay, so in this Q function for the error probability, we have this term A. 2 is a constant. Sigma depends on the noise. It is not even in our control. So the only variable that is in our control here is this A, which is the level separation between the voltage level for a 0 and a 1. And that turns out to be, for the unipolar case, the square root of twice the signal power transmitted. Now let's look at what the situation is for the polar case. So in the polar case, we are representing a binary 1 or a bit 1 as a positive voltage A by 2 and a bit 0 as some negative voltage, which is minus A by 2. Now for this, the average signal power, which again we will define as SR, and that is going to be equal to the average of the powers corresponding to a 1 and a 0. So whenever we are transmitting a 1, the average the power corresponding to a bit 1 is going to be the amplitude used to represent a 1 squared. So it's A by 2 squared. So it will be A by 2 squared. So that's the power when a 1 is transmitted, and the power when a 0 is transmitted is minus A by 2 squared, and we want to take the average of them, so it's the sum of these two divided by 2. So that gives us the average signal power for polar signaling, and that turns out to be equal to a square by 4 plus a square by 4 divided by 2. We'll get it as a square by 4. So that will be a square by 4. Now again, in a similar way as we did in the unipolar case, we can now write SR is equals a square by 4, or equivalently we can write a is equal to square root of 4SR. Right? So that's where the distinction between unipolar and polar lies. In terms of the expression, the error probability looks the same for both unipolar and polar. But what is different is, in the unipolar case, this term in the numerator, A, is representing the square root of 2 times the signal power, but in the polar case, the same A is representing the square root of 4 times the signal power. So that is where it becomes different, okay? But from the expression itself, it looks very similar, identical for both unipolar and polar. But what is different is the interpretation of this A, or what this A represents in unipolar, is different from what this A represents in the polar case. In the unipolar, it is representing the square root of 2 times the transmitted signal power. In the polar case, it is representing the square root of 4 times the signal power. Okay, now we will look at this entire thing, A by 2 sigma itself. So we're just going to focus on A by 2 sigma, right? What this A by 2 sigma represents. And to do that, we'll first square it, and then after the final step, we will take the square root again. So that will give us a square by 4 sigma square. Okay. Now, one of the things that you need to take for my word now is that the sigma square here represents the noise power. Again, that is something we'll cover in the next chapter for random processes, where for wide sense stationary process, which is the Gaussian noise, okay, the variance represents its average power when the mean is equal to 0. And because we are dealing with zero mean Gaussian noise, the variance represents its total average power. So sigma square denotes the average noise power, which we will represent as NR. So that's the noise power, which we'll call as NR. So we can write this expression as A square by 4 times sigma square is nothing but 4 times NR. And then I'm going to split this further. A square by 4 is 2 into 2 times NR. And if we go back and see from the previous page, this A square by 2 is representing the signal power for the unipolar case, and the A square by 4 is the signal power for the polar case. So that is equal to A square by 2. A square by 2 here is the signal power SR for unipolar, right? So we take only A square by 2 here. So if we take only this part, that is equal to the signal power in the unipolar case. So that is simply equal to SR by 2 times nr in the case of unipolar case. Now if we take the entire a square by 4, then a square by 4 represents the signal power in the polar case. You see, polar signal power is a square by 4. So if we take this entire term, a square by 2 into 2, which is a square by 4, that corresponds to the signal power in the polar case divided by nr. So that's for the polar case. Now we can take the square root of these terms, because a by 2 sigma, we had squared it here and we got it as a square by 4 sigma square. Now we will take the square root, so we have to take the square root of these terms as well. So a by 2 sigma is basically so that will be equal to 1 by, let me make some space here, 1 by root 2 times the square root of SR by NR for the unipolar case. That's for unipolar. And in the case of polar, it is simply square root of SR by NR. So that's for polar. So we clearly see what this a by 2 sigma represents in the unipolar case and in the polar case. We see that the a by 2 sigma is having a factor of root 2 in the denominator, and because root 2 is greater than 1, it's 1.414, that means this term is smaller compared to this term, right? So what happens is, because of that, the error probability is actually higher in the case of unipolar, and even though the error probability looks the same from the expression as q of a by 2 sigma, this a by 2 sigma is actually smaller in the unipolar case by a factor of root 2 as compared to the polar case. So to get a clear picture of this, let's see what this represents, what this means in terms of the area under the Gaussian tail. So if we have some value here, let's say we are computing the area under this part from this point to the right of this particular line here, then it's a smaller area. But if this point V is having a smaller value, then we'll have something here, and that will become a bigger area. That's exactly the same thing that is happening here. In the case of polar, we have this SR, this term a by 2 sigma, which is further to the right. So this area is actually smaller compared to the unipolar case, where it is this threshold is smaller by a factor of root 2. So the threshold is smaller to the left by a factor of root 2. That means it is giving us a bigger area here, which constitutes the error probability. So even though in terms of the expression they look very identical, in fact, in reality, the error probability corresponding to unipolar is actually going to be larger, because this threshold for the Q function is smaller in the unipolar case by a factor of root 2. So therefore the error probability is larger in the case of unipolar signaling. Or in general, we say that polar signaling has a signal to noise ratio advantage over unipolar signaling by a factor of root 2, or polar is better by a factor of root 2 as compared to unipolar signaling. So writing down those expressions again, a by 2 sigma is equal to 1 by root 2 into square root of SR over NR in the case of unipolar, and for polar the same a by 2 sigma is representing the square root of the signal to noise ratio. So from these two expressions we can clearly see that polar signaling has an SNR advantage by a factor of root 2 as compared to unipolar signaling. Signal to noise ratio advantage by a factor of root 2. As compared to unipolar signaling. Okay, and logically that appeals as well, because the noise that you're dealing with is polar. It's zero mean Gaussian noise, so noise has both positive and negative amplitudes, and to deal with noise which is polar, the transmitted signal should also be polar, so that way we have an advantage. So because the noise is polar, if the signal is also polar, it will benefit, and that is exactly what we see here in the analysis. Okay, so polar signaling has an advantage by a factor of root 2 as compared to unipolar signaling, and therefore when we do the analysis further for Emery signaling, so we'll move on from binary where we had only two symbols, either a 0 or a 1. We will shift our analysis to Emery transmission where we have multiple symbols, and each symbol is a sequence of multiple bits. So we'll have m possible voltage levels, and because polar signaling is better as compared to unipolar signaling, even in the Emery case we are going to use Emery with polar signaling. Okay, we will continue with that in the next lecture. And just to summarize everything, in terms of the expression for the error probability, both unipolar and polar error probabilities appear exactly identical, but when we look deeper into the argument of the Q function, which is the term a by 2 sigma, we can see that the threshold for the computing the area under the Gaussian tail is smaller in the unipolar case by a factor of root 2, because it has a denominator which is root 2, which is a number greater than 1 in the denominator. So the threshold for computing the area under the Gaussian tail is smaller in the unipolar case, and therefore we say that polar is better than unipolar by a factor of root 2, and hence even in the Emery analysis we are going to do only polar signaling. Okay, we will wind up here and we'll continue in the next lecture.